welcome back, and this is the UE1. It is a 1-bit vacuum tube computer that we're building from the ground up, and it's a pretty strange system. And that became abundantly clear to me when I got it up to an event and let people start seeing it and getting hands-on with it, and it was very difficult to explain the architecture and ease people into the concept of 1-bit computing. So I've been kind of racking my brain about how better to get that core concept across, and I came up with a design that got built into this PCB right here. And this was very graciously supplied by my good friends over at PCBWay, who also sponsored this episode. Now, I'm not going to show any B-roll and say, oh, they're great, go check them out. I'm going to show you the actual product. And I want you guys to look at the close-up shots of it throughout the rest of this video. Make a decision for yourself whether PCBWay is building things to a quality that meets a standard that you think is worth using. But before we get into this PCB, let's talk about why this is so weird and why I think this PCB is going to help. The UE1 here is based very heavily on the Motorola MC14500. This is a 1-bit industrial control unit that Motorola built in the 1970s to replace ladder logic in finite state machines like stoplight controllers or turnstiles or things like that. But the design was robust enough to be considered a full-fledged microprocessor. It has a accumulating result register, a full-on logic unit, and it's a pretty neat design, I think. Now, I took that design and essentially translated it to vacuum tubes and built this, but I made a couple of modifications along the way. I gave it a proper arithmetic logic unit so it can do addition and subtraction, but it still shares that fundamental 1-bit design, which is kind of a strange thing to say because it has 16 instructions. So how can you have a 1-bit computer and 16 instructions? Well, it's got multiple buses going on. There's a 4-bit instruction bus that gives us our 16 instructions, but anytime we're moving data, it all happens 1 bit at a time. The data bus is just one single bit. And that's kind of a strange thing to ease people into. It's a very weird concept. Not only that, the MC14500 and the UE1 are not considered bit slice processors. Bit slice means that you can take a lower bit width, stack up multiple copies of it, and build up larger bit widths. This is essentially how the Centurion works. It has an AM2901, which is a 4-bit bit slice ALU. So you take these 4 bits and stack them up to get however big of a data bus width that you want. But that's not how this works. It's an actual 1-bit CPU. So I wanted to come up with an idea that was simple enough to grasp and then also have that be as similar as possible to this, but as small as possible so people could get hands-on with it. And that is what this is. It's essentially a single board 24 vacuum tube version of all of this madness here. So how did I take 190 tubes and minimize it down to 24 tubes? Well, we lost a lot of functionality in the process, but the core concepts are there. So let's hop over to the bench, take a close look at this PCB, take a close look at the design of this PCB, then we'll build it out and give it a test, and hopefully it makes the concepts of the UE1 a little easier to understand. All right, let's start by taking a look at the block diagram for the UE1. And this is actually just the processor portion of it. Our data bus up here, that is our 1-bit data bus. It's gated coming into the ALU through an IEN register. Then we can do math or logic in the ALU. The output is stored in an accumulating result register, RR, or a carry register, both of which feed back into the ALU as inputs. And then the output of RR can be multiplexed, whether we have the output or the inverse output of it, back onto our 1-bit data bus. And finally, we have a write pen all the way over here on the right side of the diagram. And we use that write pen to store whatever is in the data bus into memory. After that, the only thing that we have left is a 4-bit instruction that goes into a register that then gets decoded to control everything. Then we have a collection of flags over on the right side that we use for various things. Now, when we take all of this and turn it into individual logic gates to create a logic diagram, we end up with this. It's primarily built out of NOR gates because that was the easiest thing for me to build out of vacuum tubes. And at first it looks insane, but over here on the left, we've got our 4-bit instruction register, then the decoder that decodes that out. out right here in the center, we've got our ALU, then we've got our IEN register up here, our OEN register down here, and we have a couple of extra things for the different flags that go on. All in all, pretty simple, but this comes out to 190 vacuum tubes. There's no way we're gonna make that handheld. So let's take a look at a simplified block diagram. And this is actually a block diagram for the 24 tube PCB that we've made. And you can see we've eliminated a bunch of it. We only have a 3-bit instruction now. Instead of that instruction being stored in instruction register, we just immediately decode it and use that to control everything else. Our ALU is actually not an ALU anymore. It's just a logic unit, and that gets stored in an accumulating result register. And then for our outputs, we have our gated write pins, so we can put stuff into or out of memory, and we have our result register output in case we want to use that for something else. And just like before, we have our 1-bit data bus at the top. So this takes the core concept of the UE1 and boils it down to the bare minimum. And if we break that down into logic gates, we get this. This is actually the full logic diagram for the PCB that we built. And it looks a little complicated at first, but we can break it down into pretty simple things. The 8 NOR gates over here on the right form our accumulating result register. This is just a master slave or primary secondary D flip-flop. This is what we're calling RR, and the output out of it and the inverted output out of it circle back around and feed into these 4 NOR gates over here. These 4 NOR gates form a kind of multiplexer that we're actually using as the logic unit. So A0, A1, and A2 are our 3-bit address that are selecting different instructions, and they feed in as inputs to these 4 NOR gates to create our multiplexer logic unit. The other inputs coming into this are RR and inverse RR, as well as data and inverse data. So for example, if our address is 000, the multiplexer works out in such a way that we create an AND operation. So RR needs to be 1 and data needs to be 1 in order for a 1 to get stored back into the result register. Now, if we change the instruction to 001, for example, that changes how the multiplexer is working, and we end up with an exclusive NOR operation. 010 is a no operation, 011 is an OR complement data, so it's essentially an OR gate, but data is inverse. 100 is a load operation. This just copies whatever's on data directly into the result register. 101 is an OR complement result register, 110 is an OR, and then 111 is a store. And that has to do with our write pin down here on the bottom right. This is a simple NAND gate. It's taking an input from the store operation and an input from the clock in order to illuminate our write pin to tell memory that it's time to store whatever is on the data bus. Now we also need to gate when the result register can be put back onto the data bus. That's done with this AND gate up top here. Now, whenever we're doing a store operation, we don't want the result register to change. So we have this collection of inverters and NAND gate up top here. So when the instruction is 111, we disable the clock going into the result register, which prevents it from changing. So all I did was take this logic diagram, build it out into a dual-sided PCB that ended up as this. And this is the PCB that we got from PCBWay, and I'm actually really happy with how it turned out. I did try to stick to the concept of having traces go horizontally on one side and vertically on the other side. And if we take a look at the back side, you can see it is mostly vertical traces, and right down the center, in between all of the tubes, we have pretty much every signal that is traveling through this system. And if this PCB looks a little funky, you would be right. There's a lot of interesting design choices that I made. The first is that the trace widths are 1 millimeter. The second is that the trace separation is 2.54 millimeters. But the reason that I chose these is that that is the same trace width and trace separation that I can actually machine on our mill. So all of the PCBs for the UE1 are built with these same design restraints. The only real difference is that this is a dual-sided PCB, and and all the ones that I machine are single-sided. But there's also one more glaring change that makes this look a lot different than most other PCBs out there, and that is that it is missing a solder mask and a silk screen. You just have the bare fiberglass and then the exposed traces covered with hot air solder leveling. But I just absolutely love the way that it turned out. It's really reminiscent of PCBs from the 1950s, like you would see on, say, something like the Bendix G15. But no matter what we do, a PCB is going to look a little strange when there's no components on it, so let's break out the soldering iron and fully populate this PCB and solder it up. There we go, all soldered up, and man, it came out looking real good. This looks super cool, but I did actually have a mistake that I noticed not too long ago, actually. So I had to make a little bit of a bodge. The AND gate that I built for the right pin, I had it gated by RR for some reason. That was a design fault from early on. So all I had to do was slice a trace and then hot wire one of the inputs to that AND gate directly to VCC. Other than that though, man, I just love the way that this turned out. And I love the way that these 4 switches and this push button here have been just kind of sitting on top and look really great. Now all of the tubes you'll notice are in groups of 4. That means that the filaments are powered off of 24 volts. And actually this is very low voltage, just like the UE1. I'm using plus 24 volts for my B plus and minus 12 volts for biasing. That's it. There is no high voltage anywhere on here. But it is kind of pointless if it doesn't actually work. We're trying to build kinetic art here. So let's try to get some power into this. All right, here we go. Hopefully we see all the tubes start to glow, and then we see something come up on the VFD here. If I got something wrong, the VFD might pop, or none of the tubes may glow. So let's hope I didn't get anything wrong. Here we go, flipping the switch. The VFD is illuminating something. That's not terrible. The filament isn't burning bright, so that's actually good. The tubes are warming up, it looks like. I can see a couple of them definitely look like the filaments are glowing on them. All right, it seems to kind of have stabilized into a position here. Let's flip a switch and see if something changes. Multiple things have changed. That's interesting. Okay, those all 3 seem to be doing something. That's our data. That's our clock. So let's try to load something into the result register. 100, we'll put a 1 on the data bus, and then we'll hit the clock, and it didn't load into the result register. That's not great. My clock doesn't seem to be doing anything. That's not right. All right, I definitely got something wrong here. It's going to take a little more troubleshooting to figure this out. Okay, I found at least one big glaring problem. The clock just didn't seem to be working right, so I started tracing it backwards and got all the way up to this tube right here. This is the NAND gate that feeds the clock over to the result register. And right here is supposed to be a little pull-up resistor that I forgot to solder in. So I'll put that little pull-up resistor in there and hopefully the whole thing springs back to life. All right, I think I've got it figured out. There were 2 additional problems. This vacuum tube was no good, had terrible emission. And if we look at the getter on the top, not a surprise. So this one's going in the garbage, but it has been replaced. Also, my clock here was quite bouncy, and I didn't put any debouncing in here. I also didn't put any compensating capacitors on the grids, and I really should have. So I did put a compensating capacitor on the grid of this NAND gate right here, and that seems to have solved the bounciness issue. So I think we're actually properly working right now. We can do a load operation, which is 100, and then if we set our data to 1, this should tell it to load a 1 into the result register. Now the VFDs here, the one on the far left is the result register. The one right next to it is the output of the logic unit. So the logic unit is always doing the math. The result register just stores that whenever we hit the clock. So you can see that the logic unit is telling the result register to load whatever the data bus is, because if I turn this switch off, the logic unit goes low. If I turn it on, the logic unit goes high. And now if I hit the clock, the result register has stored our 1. That's pretty cool. Now, one of my favorite operations is 101. This is an OR with the complement of the result register. So the data bus, which is currently 0, is being ORed with the result register's inverse output. So right now the result register is storing a 1. The inverse of that output is a 0. 0 ORed with 0 is 0. And if we hit the clock, we store a 0. But now the result register is storing a 0. The inverse of that is 1. 1 ORed with 0 is 1. So if we hit the clock again, we get a 1 over here. We've essentially created a toggle flip-flop through an extremely convoluted manner. So we can just toggle back and forth. How cool is that? That's really neat. So this actually seems to be working completely perfectly. That's awesome. However, it is a little unwieldy. So let's build a quick temporary base for it. I'll measure out a chunk of wood and then slice it up with the radial arm saw. Then I'll punch some holes through it in the corners and thread in some standoffs. The wood is soft enough that the standoffs actually cut their own threads and tighten down pretty well. Then we'll screw the PCB down onto the standoff so it's nice and rigid. And next I'll slice up a thin piece of hardwood on the table saw. I'll punch some holes in it and finally screw it to the top of the base plate we just built. Then we'll punch 3 more holes into this piece, and that is to make way for power terminals. Ultimately, I'm not sure how I want to power this thing, whether by battery or by Meanwell supplies or something like that, but for the short term, this at least gives me some nice banana plug jacks so that I can experiment with it and play around with it a little more without having to worry about shorting anything out. All right, we got a little wooden base made up and it's nothing fancy. It doesn't really look all that great, but it did give me 3 barrel jacks that I can put power into, which is a little less janky than trying to get it directly onto the pin headers down here. But I think this thing is fully working, so let's actually do some pretty difficult work on it. We'll do a binary addition. So a binary addition you can do with just what's called a half adder. You have operand A, operand B, and you get a sum and a carry out. So if we do 1 plus 1, that equals 2. But in binary, that is 1, 0. So the sum is going to be 0 and the carry is going to be 1. So we'll start with a 1, 0, 0 operation. This is a load operation. We're going to load 1 into it. So we're loading operand A into the result register, and we should see that light come on, and it did. That's excellent news. And then we're going to do an XNOR operation. So an exclusive NOR operation is 001, and we're going to do an exclusive NOR with operand A, which is in the result register, and operand B, which is the data bus. So we've got that set to 1. So we'll go ahead and hit the clock. Nothing changes. That puts a 1 into the result register. And now we need to invert it because operand A, operand B need to go through an exclusive OR, but all we have is exclusive NOR. So in order to invert it, I'm going to run an OR complement with the result register. So a 1, 0, 1, and I'm going to turn the data off. And so this will invert whatever is in the result register and store it back in the result register. And yeah, I did that. The result register is now storing a 0. So we want to send that out to memory. So we're going to do a 111 operation here. When I push this button, we should see this light come on. That is the write light. That's telling memory to store whatever's on the data bus, and what is on the data bus is a 0. So we just stored a 0 into memory. That is our sum. That's what we were expecting. So let's now get the carry. And so we're going to do a 1, 0, 0 and load in a 1. That should put a 1 into result register. So we just stored operand A back into the result register. Then we're going to do an AND operation. That's 0, 0, 0. And we're going to leave our data at 1. And so we're going to AND 1 and 1. The result should be 1. and our result register is still holding a 1. That is correct. So we'll go ahead and store that into memory with a 111 operation. That light came on. Interestingly, all 7 lights of our VFD are on, which is good news. That just told memory to store our carry into memory somewhere, and we just did 1 + 1 = 2. Seems very tedious to do it with switches and a push button, but if you imagine that happening at, say, 1 kilohertz or 100 kilohertz or 1 megahertz, you can actually do something pretty useful with such a simple design. Well, there we have it. Is it a full-fledged computer? No. But I think it's a pretty excellent trainer on the type of architecture that the UE1 is. They're both 1-bit, they both have logic units in them, they both have an accumulating result register that does operations on the value that's in the result register and the value that's on the data bus. So that kind of core concept of how you do computing on the UE1 is represented here on this little miniature handheld version. And I think this is going to be excellent at events. People can pick it up, get hands-on, wrap their head around how to do basic operations, and then when they see this thing chugging along with the paper tape spitting out stuff, they can really kind of start to grasp what exactly is going on with this beast of vacuum tubes. And we did it all in just 24 tubes. So I think this thing turned out awesome. Now, the wooden base is just a temporary thing I slapped together in 30 minutes to make it a little easier to handle and move around, but ultimately I need to make something a lot prettier, and I need to figure out how best to power it. I couldn't come to a decision on how to do that in this episode. I don't know, I'll come up with something that looks pretty, we'll stain the wood, make it look real nice, and so that way, at the next event, somebody can pick it up, get hands-on, and wrap their head around exactly what's going on with the UE1. So I want to thank PCBWay so much for sending me these boards. Hopefully you guys saw enough close-ups of them and saw them in action so that you could make an informed decision yourself about the quality that PCBWay can produce. And, well, most importantly, I want to thank you guys so much for watching, and I hope to see you in the next episode.